This is the equation of a neural net, the fundamental building block behind all of AI. On the right side is a function of some inputs that are passed through several layers of functions to make a prediction for that input. The layers of the neural network depend on some parameters, denoted here by theta. Most modern neural nets have many layers, but here for simplicity, our example has just two. When training a neural network, we start with known inputs and outputs and try to find the parameter values that minimize a loss function applied to the predicted output and the known output. Importantly, we think of this function as a function of the parameters. We typically have an existing set of parameters from which to start. We'd like to iterate on the existing parameters to find parameters that decrease the value we get when we evaluate the loss function. The fundamental step in iterating on the parameters is to compute the derivative, or, as it is sometimes called, the gradient of the loss function with respect to the parameters, and move the parameters a little bit in the opposite direction of the gradient. This derivative can be computed via the chain rule, but the application of the chain rule is a little complicated due to multiple appearances of the parameters in the equation. Here is that application of the chain rule in the simplest case. Consider two functions of two variables and their composition like this. The derivative of h with respect to theta is the sum of the derivative with respect to the theta in the second argument of f, and the derivative with respect to the theta in the second argument of g. This can be rewritten in this notation. Note that the functions f and g have two sets of arguments, the first of which we'll call coordinates, which in the neural net example are either the inputs or the internal layer outputs of the network. And the other arguments will receive the parameters. For example, this derivative is with respect to the coordinates, as you can tell, since the subscript is g plugged into the coordinates position of f. Here we're shortening g evaluated at x0 and theta0 as just g theta0. And these derivatives are with respect to the parameters, as you can tell by the subscript theta0. This notation will help us succinctly express the chain rule for neural networks. In a two-layer net, the derivative of the loss function would be this. As you can see, this derivative can be computed iteratively. First, by computing the derivative of L evaluated at the output layer, then computing the derivative of the final layer, both with respect to the parameters and with respect to the coordinates, and so on for each previous layer. This process of computing derivatives, starting from the final layer and working backwards through the network, is called backpropagation.